Got another minute.
Okay, another couple minutes. Okay, so don't look over here. So here are three astrophysical calculations. And actually on the left, we're showing development of large-scale structure in the universe. If you can see the number in the lower left, that's billions of years before present. It's a countdown. But I'm going to show you a higher res, more recent calculation here, so let's not pay a whole lot of attention to that. But basically, these blobs here are galaxy clusters. So there might be like 1,000 galaxies in one of these guys, all orbiting each other. Right. So you got all these. So these are bound galaxy clusters. So they're actually all orbiting each other. Sometimes they crash into each other. So in the center panel, we have two colliding galaxies. So this is what's going to happen to the Milky Way and Andromeda in about 2 million years. Right? Andromeda's coming at us at a couple hundred kilometers a second. So we're going to collide with it. Both Andromeda and Milky Way are big spiral galaxies, kind of like this. And this simulation was set up to kind of mimic the collision trajectory, kind of the angles of the galaxies and the trajectories. So this is what we think is about going to happen.
When that happens, do stars smash into each other?
No, it's almost entirely collisionless. So the stars are so small compared to the sizes of the galaxy, they basically pass through one another. Very, very few stellar collisions. They're just going too fast and they're too spread apart. But they really interact gravitationally. And a big mass of the galaxy is gas, so the pink-orange stuff here is gas that hasn't formed stars yet. The gravitational interactions tend to trigger star formation, so these big sprays of blue particles, those represent sites of star formation. So they don't represent individual stars. Each blue point here represents something like 10 to the 4th to 10 to the 5th stars. These are kind of areas where we expect to see star formation.
You include dark matter?
We do. So we crucially include dark matter. It doesn't work without dark matter. And so this is all dark matter here. And most of the mass here is dark matter. And what's governing the whole dynamics here is the big dark matter halos that are interacting gravitationally. And the matter that you see here is just kind of along for the ride. Okay, and then finally we also include black holes. So it's thought that most spiral galaxies have supermassive black holes in their cores. And so if these galaxies coalesce, the two black holes will relatively quickly sink to the center of the potential. And on the right we have a model of two colliding black holes. So the black holes will end up orbiting one another, and this is showing the last few orbits. We're showing the event horizon as these striped spheres. We put stripes on them so you can see the rotation. And the orange and yellow contours, are contours of curvature in space-time. So
these are actual singularities, unlike our singularities.
Yes. So these are actual singularities, though they're hidden behind the event horizon. And it's actually really hard to move these through the computational grid because they're singularities, everything breaks down there, and when you move them, you don't kind of know what to fill in behind them. They kind of leave this crazy wake. But there was a big numerical breakthrough. They figured out how to do that. And you can see the kind of what's called the Coulomb part of the field around each black hole when they first start orbiting. That's kind of the potential throat, the big gravitational field around each black hole. That's these kind of big structures. But when they plunge together, you'll actually see propagating waves. And this is gravitational radiation. So general relativity predicts traveling solution, so you can kind of start to see these kind of waves developing, and then there's a big flash of gravitational radiation traveling out at the speed of light. And this is what we hope to detect with missions like LISA. It's the space-based interferometer.
So the result would be